Hi everyone, I'm Shaojie, a PhD student from Professor Zhang's group at Cornell. Today, I will present HeteroFlow. This work is in collaboration with my colleagues Yi-Hsiang, Yuan, Hongzheng, Niansong, and Debjit. FPGAs offer an attractive platform for custom hardware acceleration because they can provide massive parallelism, flexibility, and also high performance per watt. FPGAs have been adopted in mainstream cloud service providers like AWS and Intel. They are also widely used in edge applications. However, FPGA is known to be extremely hard to program. FPGAs have the custom memory hierarchy and custom compute units. It requires programmers to have in-depth hardware expertise to combine different types of hardware customization techniques in order to get a high performance. Let's take a closer look at the hardware customizations for FPGAs. In general, there are compute customization, like unrolling or pipelining, to increase the parallelism. Data type customization, like quantization, to trade off precision with performance. And also memory customization, like memory banking, reuse buffer, to increase the bandwidth utilization for both on-chip and off-chip memory. In fact, these different types of customization techniques do not just work in isolation. There's complex interdependence among these techniques. Perhaps the most important aspect of this interdependence is how the data is placed and moved between this custom storage and compute kernels. We use the term data placement to address this interdependence between memory and compute. Data placement is crucial to performance. However, it is not an easy task to optimize data placement on FPGAs. First, FPGA has a complex memory hierarchy, and the data placement can happen at different levels. Specifically, as FPGA programmers, we need to take care of data placement between host and accelerator, data placement between kernels inside the accelerator, as well as the data placement between processing units inside a kernel. We should ensure the data of right granularity arrives in the right memory location at the right time. Additionally, data placement do not just work in isolation. To get a high performance, we need to co-optimize data placement with hardware customizations in compute, memory, and data type. Here, we use image blur as an example to illustrate the data placement optimizations in HOS. Image blur consists of two back-to-back convolutional 1D kernels. Here, let's look at the HOS code with the optimized data placement. HOS programmers need to insert vendor-specific pragmas, restructure the code in different ways to optimize data placement at different levels. For example, here, for the Host-Accelerator data placement, they need to insert the interface pragma and to choose the right burst length. And for the Intra-Kernel data placement, they need to instantiate FIFOs and connect them between kernels. And for the Intra-Kernel data placement, they need to instantiate different processing units and make sure the fine-grained data movement is correct. From the code, you can see that in HOS, there's not a unified programming interface for data placements. And data placement is tightly coupled with the algorithm, making the HOS code less portable and less productive. To address this limitation, we propose HeteroFlow. It's a new programming model with decoupled primitive for data placement. HeteroFlow is built on HeteroCL, a popular domain-specific language for FPGAs. HeteroFlow inherits the declarative programming paradigm and decoupled customizations in compute, memory, and data types from HeteroCL. Here is a simple code example in HeteroFlow to realize the 1D convolution kernel. As you can see, the algorithm at the top is decoupled from the customization at the bottom. The algorithm, in the algorithm, we use the declarative paradigm to specify the algorithm of a 1D convolutional kernel. We further extend HeteroCL with this new .2 primitive as a unified programming interface for decoupled data placement. This .2 primitive captures the interdependence at different design levels between memory and compute. And we will show more details in the following example. Here, we use the image blur example to demonstrate the usage of .2. In the code snippet, we first define the algorithm of the 1D convolutional kernel. And later, we instantiate 2 convolutional kernels to build a complete image blur application. In the last line, we create a schedule and map this schedule to the target accelerator platform. Here, we haven't applied any data placement customization yet, so this application is by default placed to host, as shown in the hardware paradigm on the right. For the next step, we can use this .2 to specify the data placement at Host-Accelerator level. As you can see, for the last 3 lines, we first import a platform that includes the host and also the accelerator platform. And later, we use this .2 to move the image weight from host to accelerator, and we move the output from the second 1D convolutional kernel from accelerator to host. By doing this, by doing this, these 2 1D convolutional kernels will be automatically inferred to be placed on the accelerator. And furthermore, we can specify the data placement between these 2 1D convolutional kernels. As you can see, in the last line, we use .2 to stream the output from the first kernel to the second kernel. By doing this, we create a FIFO between these 2 kernels, which gives us better throughput. We can further use this .2 to optimize data placement inside a kernel. Here, for this 1D convolutional kernel, we choose to map it to a systolic array architecture, which provides better performance. To achieve this goal, we first define the algorithm of this 1D convolutional kernel, and then we use this unroll primitive to unroll this reduction loop into 3 PEs. And we can use this .2 to broadcast our input image to all these PEs, and then we use .2 and cascade .2 to propagate the partial sum from one PE to another. Here, we are propagating the partial sum from PE0 to PE1 and finally PE2. With this .2, we are able to build a weight stationary systolic array for convolutional 1D kernel using just a few lines of code. In addition to the use cases we just mentioned, the .2 primitive can actually cover a comprehensive design space of data placement, as shown in the table. With this .2, programmers can customize data placement at different design levels with different communication schemes, again, in a decoupled way. Here, for example, for the host accelerator data placement, we can choose between cache or DMA mode. In cache mode, it's better for the arbitrary data access, and for DMA mode, it can be used for sequential and arbitrary data access. Similarly, for inter-kernel and intra-kernel data placement, you can choose from the stream, single buffer, and double buffer mode to explore the trade-off of between performance and area overhead. This .2 primitive enables programmers to explore the design space of data placements, and it also makes It's much easier for it also makes it much more productive to combine data placement with other hardware customizations. Here we show some more common use cases of DAO2 in realistic applications. This figure shows a typical CPU FPGA hardware diagram. For the host-accelerator data placement, we can use the DAO2 to stream the sequential data access from host to accelerator with the stream mode. Alternatively, we can also use the DMA mode to move data the other way around from this accelerator to host through the device memory. For inter-kernel data placement, DAO2 can help you create a double buffer for inter-kernel communication, or you can use DAO2 to create multiple FIFOs that can broadcast the data from one kernel to other kernels. As for the intra-kernel data placement, we can map the loop nest to systolic array architectures of different data flow patterns. As we have shown in the previous example, you can cascade DAO2 to specify the data movement between the processing units inside a systolic array. For more details, please refer to our paper. We built an optimizing compiler to compile HeteroFlow code into high-performance HOS code. From a high-level point of view, the input HeteroFlow program is first lowered to a data flow graph representation, where each node is a compute kernel, and each edge is the input or output data of the compute kernel. If the kernel or the data is not placed explicitly using DAO2, it's marked as gray. For the second step, HeteroFlow compiler will automatically infer the placement for this gray node and edges, with the goal to minimize the total off-chip memory access. And after that, the compiler will automatically partition the graph into host and FPGA scope, and it will automatically apply I/O optimizations, including I/O scheduling and memory banking, to improve the memory efficiency. Finally, the optimized DFG will be further used to generate optimized HOS code, which can be later deployed to different FPGA platforms, including Xilinx and Intel FPGAs. Here, we use optical flow as a case study to evaluate HeteroFlow. Optical flow is a classic video processing algorithm. It consists of 8 kernels. To achieve high performance, we need to access the data from host to accelerator in a packed format, which gives you better off-chip memory bandwidth efficiency. And to improve the throughput, we need to further create a streaming or FIFO channels between the kernels, which can give you better throughput. And we can use HeteroFlow to capture the optimizations for these 2 levels of data placement. Here is the HeteroFlow code. On top of the algorithm definition, we use the DAO2 to move the packed data from host to accelerator. And later, we move the output from accelerator to host. This customization will generate the HOS code on the right-hand side. As you can see, HeteroFlow compiler will automatically infer the right interface pragma for you. And we also use the DAO2 to connect kernel with FIFOs. This will be used to generate the HOS code on the right-hand side, where it has the stream pragmas and also the right connection between different FIFOs, between different kernels using FIFOs. Here's the result. By using HeteroFlow, we can use much fewer lines of code to achieve similar and even slightly better performance compared with the manually optimized HOS code from Rosetta benchmark. More importantly, the same HeteroFlow code can be retargeted across different FPGA platforms with minimal efforts. Here, we retarget the HeteroFlow code to Xilinx U280 and also Intel Stratix 10 FPGAs with only a single line change of code. And this can give you, the same program can be targeted to different FPGAs and give you similar performance. We use the Ultranet as another case study to show how HeteroFlow can be used to build a complicated 2D systolic array, and how we can use HeteroFlow, the new DAO2 primitive, to connect systolic array kernels with non-systolic array kernels and build a complete accelerator design. Ultranet is an object detection neural network, and it's the winner of DAC SDC Contest 2020. In the original HLS implementation, there are 9 layers, and they're connected with FIFO channels. In HeteroFlow, we use HeteroFlow to re-implement Ultranet. To further improve the performance, we replace the 3rd layer in Ultranet with a 4x4 output stationary systolic array. And here, let's look at how we can use the DAO2 to create a systolic array and connect it with other non-systolic array kernels. Here on the top, we have the declarative APIs to build the algorithm. And at the bottom, we first use this .enroll to create a 2D array of processing units. HeteroFlow compiler will automatically generate data loader and data drainer to improve the communication efficiency. And later, we use this .2 primitive to propagate data across this PE for better local data reuse. And next, we use this .2 to stream data from the previous layer and to stream the output of this 3rd layer to the next layer. By doing this, we can create a high performance output stationary systolic array for the 3rd layer. Let's look at the result. Compared with the manually optimized HLS code, the HeteroFlow version uses much fewer lines of code, and we can achieve much better performance with this more processing units for the kernel implementation. We can achieve in total 1.31x speed up compared with the manually optimized HLS code, which is quite impressive. To summarize, HeteroFlow is the first programming model to provide a decoupled programming interface for unified data placement. And yeah, we are able to connect systolic array kernels with non-systolic array kernels to build a complete design. The key takeaways: HeteroFlow is the first programming framework to provide a unified interface for decoupled data placement on FPGAs. HeteroFlow also enables the co-optimization of data placement with other hardware customizations like tiling or quantization, which makes it much easier and more productive for you to build complete designs. HeteroFlow provides you better productivity, performance, and also better portability. You can target the same program to different FPGAs with minimal efforts. And we are open sourced. Yeah, the code is publicized. If you are interested, we welcome you to check out our code repo. And yeah, thanks for listening.